route jointly with my two PDRAs, Juana Lang and Alexandra Lobe, also joined with Peter M. Van Loven from Colorado and Roland Potthast from DWD. Okay, so I normally explain what the filtering problem is, but there is no time. All I'm going to say is that the filtering problem aims to kind of estimate the a hidden component, and I'm sort of pictorially I'm presenting here this a state space model which takes value in some high dimensional state. We're currently working with 1 million dimensions or thereabouts. And then you have some observation, some partial observation of this hidden state. This is your data, and what you want to compute or approximate is the conditional distribution of this process, which we call the signal, with respect to the observational data accumulated over time. And this is we call the posterior distribution. And the way in which I represent it is by these blobs of mass that move through space. And the state space is sort of always part of the support of the posterior distribution. And here there's the model, and I'm not going to spend time on telling you what the model is. The thing is, you do your data assimilation, you do your filtering starting from some time, nominal time 0, and you evolve it in time. You evolve in time your posterior distribution by using your observations. But before you get to do that, you have to have a model, and you have to calibrate the model. And it is this part that I'm going to talk about today. I'm not going to talk about data assimilations or filtering. I'm going to talk about calibrating the model, in particular calibrating the stochastic parametrization. And for this, we will need samples from the model, and I'm going to explain how you get these samples in what follows. Okay, so now why do you need stochastic parametrization? And this is taken from a paper which appeared in the American Meteorological Society in 2017, and it has a large number of people that signed on this paper. So it's this is not something that I wrote. I love it because it makes a strong case for the use of stochastic PDEs in numerical weather prediction. Is written by all of these papers, and if you can see it, you should be able to recognize most of them. Okay, so what I'm saying here is that numerical weather predictions and climate modeling is based on discretization of some continuous equations of motion, read PDEs, and these are embedded. These are numerically simulated in some dynamical core, which describes the resolved scales of motion, including physical parametrizations, and they will give estimate of the processes at the level of the grid scales where the discretization is done. Beyond that, this cannot be done. They cannot be resolved. And so far, this approach has been very successful in weather and climate, and people do have very good forecasts with high skills in this area. However, it has become apparent that there is a bottleneck there, that there are systematic shortcomings due to the fact that the unresolved processes are not properly represented. Okay, and there's a lot of physical processes which are there, and they are not, they cannot be captured by these numerical implementations of the PDEs. And on top of that, you would like to be able to ascertain the uncertainty of the model. And you can't do that by using the PDE approach. As a result, you have to resort to stochastic parametrization to estimate uncertainty and reduce the systematic model error that comes from the unresolved scales and all these other things which are enumerated in there. The bottom line is, and this is really a subtitle of the paper, of this paper that appeared in the American Meteorological Society, is that stochastic parametrizations empirically derived or based on rigorous mathematical and statistical concepts have great potential to increase the predictive capability of next generation weather and climate models. Okay, so this is something which we embrace, and as somebody that works on stochastic PDs, I love it because that means that what we do makes sense from an application perspective. Okay, so now I'm going to explain how we incorporate stochastic parametrization, and then how do you end up with an SPDE rather than a PDE, and then how do you calibrate that stochastic parametrization. So the way I do it in a very generic form, and then I'll give you some examples, but you will see that I hope to make the point that this particular calibration technique that I will present can be applied to any example that you encounter in numerical weather prediction. So in general, let's suppose that we have a GFD model, which is a solution of a PDE. So you start with a PDE. And I'm writing this as a PDE, where A is an operator defined on a set of functions and so on. But this is just to start with a simple form of your PDE. And we are assuming that this is a high resolution model. We're assuming that this is a model for your small scale, your high resolution simulations that you have. And what you want to do, you want to say, okay, I'm not going to use this high resolution model. I want to use a low resolution model. Right? Because of that, because you're going to use a low resolution model, you will have unresolved scales. How do you model these unresolved scales? You will add to it a stochastic term. And I'm writing this stochastic term in this form here. Okay, this is added to your PDE. You end up with an SPDE here. Okay, and I'm trying to explain what this is here. So M here is going to be another operator, and I'm going to give you some examples of operators. Okay, and then WT here is a cylindrical Brownian motion. And for those of you that know about this, it can be an infinite sum of one-dimensional Brownian motion modulated by some fields here, psi k, which depend on the space, right? So these are space-dependent vector fields, and these are one-dimensional Brownian motion. And the object of the parametrization is to estimate this psi k. So what I will explain is how do you estimate this psi k under the assumptions that you know what A is and you know what M is, modulo this psi k. And this is the simplest example that you can think of in geophysical fluid dynamics. You take the 2D Euler equation in vorticity form. You can write it like this, where omega is the vorticity and u is the velocity. You can write it. The operator that you have in here has this specific form. I'm not going to go through the details. It's just that to show you that that's what you have in general. And then you can say, okay, now how do I add in stochastic parametrizations to this particular PD, to the 2D Euler equation? Well, there's lots of ways in which you can do that. You can have something which is additive parametrization. You can just add your cylindrical Brownian motion, or you can have something which is multiplicative, or you can have transport parametrizations, and there are many, many others like that. Okay, the methodology that I will present to you applies to any of these type of parametrizations and applies to any PD that you encounter in geophysical fluid dynamics. Okay, now I would make the point next that it's important to do this stochastic parametrization, to add this stochastic parametrization, because the influence of the small scales is massive. Okay, so I'm going to show you next. A simulation. Let's see if this is working. So what you see here an evolution of the Euler equation, right, in a box. And here is the evolution of the velocity. Here is the evolution of the vorticity. Okay, so this is on the small scale, on a refined scale. Underneath here is the same run on the coarse scale. What you should see in here is that very quickly they start to differ. They don't differ just because of the modification of the coarsening, but they differ fundamentally. The effects of the small scale accumulates over time and they get quite far apart from one another. So that's it. That is why you need to account for the small scale by doing something, for example, by adding stochastic parametrization. Okay. Right. What is the general principle of the stochastic parametrization, the calibration that we developed? What you do, your data is the solution of the PD MF, and what you do, you get the modifications of that. For example, you apply a low pass filter to that. You take the difference between the solution and the modification. You get this process M hat, which is supposed to kind of incorporate the effects of the small scales. And then you look at the increments of this process, and the increments of this process, you make the ansatz that they'll look like this, which is exactly the stochastic term that you apply in the first place. Okay, so that's your ansatz. Okay, these increments will look like this, a list in distribution, which you can approximate in this way. And then the next step is to compute this psi k by using a principal component analysis. That's it. This is in a nutshell what we do, right? You know, it looks very simple, but there's a lot of work in order to get the psi k out of these term increments in here. And so the remarks that I like to add in here is that when you solve the PD and the SPDs, that these are theoretically defined on the same physical domain, but when you numerically approximate them, you approximate one on the refined grid and the other one on the coarse grid. Now, the calibration procedure is agnostic to the source of input data. In what we will do, I'm going to show you how we do this by using synthetic data from a model that is run on a refined grid for a sufficiently large time window. But this can be real data coming from reanalysis. So this is where the reanalysis will play a role. We extract data from the reanalysis and apply it here to do the calibration. Okay. Now, the way in which the results depend on the choice of the perturbation, on the choice of the stochastic parametrization. You'll get different size for different choices of this, right? But for all of them, you can essentially apply the same steps that I enumerated above. Okay. Now, I'm explaining here what you do in the case when you have an additive noise. In this case, the applications is almost straightforward. You just do the increments. You look at the increments of the M hat, and in this case, the increments will have approximately a normal distribution with a sum, which depends on the psi k, and then here it's straightforward to apply principal component analysis to compute both the psi k and the number of psi k themselves. Okay, so there's lots of things that have to be added in here. You know, you have to make sure that you decorrelate the data so that you get independent samples. The PCA involves computing covariance metrics, the sample covariance metrics. And the most important things to realize here is that the psi k's depend on your data. The psi k's are data dependent, okay? And you need a lot of data to compute the psi k, and it's not a parameter estimation. And that by saying that, I'm saying that because the psi k depend on the data, that means that you can have different psi k when you use different data, and they all will work. Right. So what is the model that we looked at? So this is the stochastic rotating Charlotte equation. So you start with a deterministic model, which depends on, which is the evolution equations of the velocity field of two-dimensional fluid and the height. And I'm explaining here what the height is. And you just have to take my word that the height is what it is. And I'm just going to flash the model in front of you because I need to get to the actual simulations. You know, everything is explained in details for people that want to see here. We have a term that incorporates the effect of the rotation and a term that incorporates the effect of the gravitation. And you can write it in this form. And here I'm explaining many things why this is a good model to test. It comes very close to the primitive equations, which is the equation used in the numerical weather prediction, and it has a lot of other nice properties. And the next step is to explain how you get this stochastic parametrization. And there's a lot of work in here. There's a lot of mathematics in here. And this is not an obvious, trivial stochastic parametrization. At the basis of all this is this idea that you add stochasticity to the Lagrangian particles, not to the Eulerian picture. Okay, and this has been advocated by my colleague at Imperial, Daryl Holm, in 2015, and there's been a lot of work since then from him and from myself and my collaborators. This is how the stochastic parametrization looks like at the level of the SPD. So you have the deterministic part, but you have a stochastic part added to each one of these, right, in terms of operators that are definitely far from the additive noise parametrization. It's really very complicated, but the claim here is that this is a physical stochastic parametrization. And this leads to an SPD that has is well posed and so on and so forth. Okay, so now let me give you the results. So the PD is run on this fine grid, okay, and then we have to wait for 1,000 time steps to get something which looks sort of reasonably interesting. And then here I'm explaining again what we do in this case. This is a far harder application because it's not immediately obvious how to get to the psi k, how to get to the data. So there's a lot of work in here that we've done, but I'm gonna jump over this. I want to just show you the results. So the results. So we have 8 experiments in here. First of all, the first thing is we explain 90% of the variance. So when you do the PCA, you have to decide how much of the variance you're going to explain, either 90% or 99%. So you will have more noise added if you want to explain more of the variance, and in the case of 99%. And then when we're going to run the simulations of the SPD, you will see simulations with 50 realizations of the SPD and 100 realizations of the SPD. And then when you do the coarsening is done from this fine grid to this choice of these 2 grids. 256 by 40 and 556 by 80. We divide everything by 4 for this one and everything by 8 for this one. That's the coarsening that is done. So for each of these choices, we have one experiment. So the first thing that I'm going to show you what the psi k are. So the psi k are these fields which are obtained via the PCA from the data. So this is the first one. This is the one that explains most of the variability. Right, and you can see that it has a lot of core scale features, right? And when you go to the last one explains a lot less, but it has a lot of small scale features. So these are the psi k's that appear in front of your Brownian motions. That's how they look, and there's 9 different psi k coming up one after the other. Now, what I'm showing you here is we've done the calibration, and now we compute independent realization of the SPD. What you see in the middle, so we took two points on the grid, on the coarse grid, and we identified these points on the refined grid, and we looked at the realization of the PDE, and then we compared the realization of the PDE with realizations of this SPD. So this is for the elevation, this is for the zonal velocity, and this is for the meridional velocity. So what you should see in here, essentially, that the PDE runs smoothly, the HPDE, it gets perturbed, but essentially stays close to the PDE, and there is a spread. Because you want to have a spread when you do the data assimilation. Is the big problem there. You have to have enough spread in order to be able to spread the particles and also let the particles survey the underlying space. Here, the spread is done automatically by the stochastic parametrization. Okay, so now we look at the ensemble spread, right? So this is the thing that is really very important, that really says whether a particular parametrization is good or not. So when you look at that, and what you see here, you see 4 sets of 2 pairs of realizations. Now, these 2 at the bottom, these are the spread corresponding to the 90% of variability and corresponding to the coarsening the grid by 4. So here you need the least amount of stochasticity, therefore the spread is smallest. Okay. The next one is when you coarsen the grid by 8, and you get this. And then the following 2 is when you coarsen the grid by 4, respectively 8, and then you want to explain 99% of variability, right? So the most randomness appears when you explain 99% of variability, and you have the coarsening of the grid by 8, which is quite understandable. You can see that the spread is fairly stable, and this is true both for the elevation, for the zonal velocity, and for the meridional velocity. So the stochastic parameterization does the job correctly. The RMSE, the RMSE is tells you a similar picture. Again, we have stability. 5 minutes. You have stability in the size of the RMSE, and again, the biggest effect is coming from having to explain 99% of the variability. Increasing the number of particles from 50 to 100 has the least effect, right? So that means that already when you have 50 particles, you have enough spread. You won't get more spread if you increase the number, if you double the number of particles. And for the relative L2 error, of course, these are things, you haven't done any data assimilation, so there's no correction mechanism. So you should expect things to keep increasing, right? But once you start applying the data assimilations, you stabilize the L2 error, and so in this case, it's natural to see things increasing. This is not the case for the elevation. We can't explain why the elevation is decreasing towards the end. Presumably, it's going to go back up after that. Okay, so final remarks. What we did, we introduced a generic calibration method that can be applied for any stochastic GFD model. So you choose your model, you choose your stochastic parametrization, and this can be calibrated by what I explained in here. This calibration is Eulerian in nature. That means you need to have when you get the data has to be available to you at all points on the grid. This is different from what we did before. We did Lagrangian calibrations where we calibrate by looking at what happens to the Lagrangian particles. So we have a paper jointly with Colin Cotter and my PDRAs. This calibration can be applied to any type of stochastic noise, additive, multiplicative, transport noise. The one that we favor is the so-called salt noise. Salt comes from stochastic aberration by Lie transport, and we've been working a lot on these things and try to explain why this is a physical calibration as a physical parametrization as opposed to the one that are enumerated above. This parametrization generates a suitable ensemble spread for the coarse grain true state, and that means that you can then use this for your choice of data assimilation techniques. This is all in preparation for the forthcoming observational data from the SWOT mission. And if people want to see what this means, they can look at the NASA website. The point I'm going to close up with this. Do not try to apply additive parameterization. It doesn't work. And we have in the paper, we explain in the paper, why is that? You end up with very small spreads because this is not physical. Okay, so last but not least, we have a running program which is sponsored by the European Union. We got this before Brexit, and so I think we were the last ones, and then the door closed after us. If people are interested to talk to us, we do a lot of work. We have a lot of activities. It's called the Synergy Grant, and you just have to type steward, and then you will find it there. This is jointly with INRIA and IFRMR. There are 4 PIs, myself, Bertrand Chaperon, Dario Holm, and Etienne Memin, and we have a very ambitious plan. We're about halfway through the project, and there are many ways for people to interact with us. Just send us an email and we can discuss. Okay, so I'm going to stop here. I'm going to just show you a few of my papers on related to the topic that I discussed. Thank you very much.
Okay, thank you very much, Dan. Any questions?
Thank you. Can I just ask a really basic question? I think I missed this. Where did you get the data from to do the PCA?
Yes. So in this case, we used synthetic data. We ran the PD. We ran stochastic, the rotating Charlotte equation on a very refined grid, recorded this, and applied the calibration methodology. That was it. We did synthetic data. But of course, you can use the analysis data and do the same thing.
Okay, any other question?
Yeah, sorry. Can you explain again so you say you have 50 or 100 particles, but I was not very clear on where does that diversity come? And I think you mentioned, it's kind of a second part, you mentioned you can use observational data, but there you would have observation noise as well. And so would it be easy to kind of decorrelate the two, to basically learn really only the noise and the dynamics and without being influenced by the observational noise?
Okay, so once you calibrate your SPD, right, you know exactly what this term is, and then when you run the particles with independent realizations of the noise. So that's how you get the spread. You just run independent realizations of the noise. That's all you do. Now, at this point in time, I have not started to do my data assimilation. All I did is just make sure that this calibration have enough spread so that I can begin to do the data assimilations and use observations, partial observations with noise or without noise and so on, to try to, select the one that are the right one and weight them and so on and so forth. So at this point, there is no observations. I'm just calibrating the SPD, and the spread comes from having independent Brownian motion. So we can have 50 independent realizations of Brownian motion, or 100 of them. And the point is the spread does not increase, which means that you're going to be okay to use something of 50 to 101. You will not have to use a larger number of particles when you do your ensemble data assimilation.
Okay, well, I think in the interest of time, we can thank Dan again.